Okay, good morning class. So today we're looking at trigonometry problem solving, 2D and 3D problems with the 2-dimension and 3-dimensional problem. Alright, so now we're going to look at examples for exercise 3. And exercise 3 is on page 126. Okay. So let's read. Problems in 3 dimensions. 3-dimensional problems can be complex because you are working in 2 planes, a vertical and horizontal. Right angles do not always look like right angles. The diagrams below represent 2 typical 3-dimensional diagrams where AB is the vertical height and B, C and D are in the same horizontal plane. The horizontal plane is shaded. Okay, so to me the horizontal plane I would always consider to be the ground. You see him? As being the first one. Okay, this is now assuming that you have a triangular floor, and this is the, like in a room, this will be the wall or the height. Can you see that, people? Now, if you look at this here, the wall and the ground, okay, without the, what's his name now, what do you call this, the skirting, no? You got the wall and you got the ground. The wall always stands 90 degrees to the ground, not so perpendicular, unless you're now on the leaning tower of Pisa. No? Is that the right word I say? I just didn't take note in history, I was doing my maths homework. But anyway, so the floor will be perpendicular to the ground. That's for maximum strength. Okay, that's the reason why. Because if it's now at an angle other than 90, then they will be leaning, which will then put strain on the weight. But anyway, so the floor under normal circumstances, if you're building right, or your builder is doing the right thing, the ground will be 90 degrees to the wall. Not so. Likewise, if this is the ground, the horizontal plane, it's flat, and this is your vertical plane, you're standing up. Now, you see here, this forms a 90 degrees to the ground. Can you see that, people? Although this angle doesn't look 90, and there we go vertical, and the one side of the triangle, it's also 90. That is why they say it doesn't look 90, but it is 90. Okay? So that's a typical 3D diagram, or this is the other one. Okay? There's not much that they ask you here. This is why this is so easy. The section is easy to get 10 marks. Okay, you just need to master it, and then you always will be getting your 10 marks to the section. Okay. Again, here's your ground, the horizontal plane. It's always shaded, as you can see here. And then to the ground, you have your vertical tower there. AB is your vertical. Okay. Then AB will stand 90 degrees again to the ground. You guys understand? Let's carry on with our lives, no? First problem. This is the example on page 225. Example. Page 225. Huh? 125. You don't get upset. Right. Any Sheilas here? Not in this class. Okay. Sheila and Desmond stands. Sheila and Desmond stand some distance away from the building AB. Okay, so Sheila is at the C and Desmond is at D. Okay. Away from the building AB that has a height of 12 meters. You see the height is 12 meters. The foot is most at the bottom, not so. So the foot of the building B, Sheila and Desmond are in the same horizontal plane. So in other words, the foot of the building is on the ground, no? The bottom, the part that you see. You know there's a foundation under the ground, no? Right. The part that you see is the foot of the building. Okay? Sheila and Desmond standing on the same horizontal plane, so it's all on the ground basically, no? The angle of elevation, so this is the angle that's going up, from D to the top of the building A is 40 degrees. And from C to A, the angle of elevation is going to be, is given as 45 degrees. Then we are told that CBD is 55 degrees. Calculate the distance between Sheila and Desmond. So in other words, we must calculate CD. Now, people is not going to work straight away for 10 marks or 8 marks, calculate CD. And you're going to use the sine rule or the it's not going to work like that. There's other lengths you need to calculate. But if you look at CD, you know that CD is in triangle CDA. In other words, if I can calculate that length, if I can calculate that length, and I must work on that angle there. Or I need to have another angle here somewhere. If I have that angle, which rule can I use here? Two lengths and included angle, cos rule. If I had any other angle, sine rule. But this 1, 2, 3 part piece of information I must calculate. Not so. Which is a lot. Okay, and we lazy people, not so. So you look at CD, where else does CD fit in? In triangle CDB. So what do I need? I need BC and I need DB. But what do I have? An angle of 55 degrees. You see that, people? So at least I got one more piece in there in comparison to the other triangle. I highlighted it first. You see that, people? So, can I calculate BD? Can I calculate BD? Which triangles is BD in other than BDC? ABD. Can I calculate BD? Well, what angle? What's the size of this angle? 90 degrees. So hang on, we're onto something. We can calculate BD. Okay? So let's go with BD quickly. So what I'm going to do is I'm going to take that out and show you how it looks. Okay? So there's, remember that's 90. I'm going to draw in the 90 there. 90. 12 AD 40. So what do I say? I say in triangle ABD. What can I say? I'm going to calculate the adjacent, not some. So which trigonometric function is opposite and adjacent? Tan. So tan of 40 is equal to 12 over BD. That's naturally over 1, cross multiply. So that's going to be BD tan 40 is equal to 12. So BD is equal to 12 over tan 40. And that works out to be, okay, for those of you opening calculators for the first time for the week, it's going to be 12 over tan 40. And 40 gives us an answer 14.3. You guys got that?
Yes.
Looks like you guys are going to pass now, no? That's going to be 14.3 meters. Okay. So, looking at the other triangle, what did we say we still need? BC. Now we got the triangle looking like this now. What do I have in this triangle? I have 45. What's the size of this angle here? 90 degrees. So I can calculate BD. This is what you should be seeing. This is A, B, C. This angle is 45. This angle is 90. This is 12. So which trigonometric function uses opposite and adjacent? Again, tan. Tan is popular, no? Everybody wants to be tans for it now. Okay, so that is in triangle ABC. So what can I say? Tan of 45 is equal to 12 over BC. We know this is 1, so BC is 12, no? Okay, but let's act dumb and we don't know that, okay? So we cross multiply. So BC tan 45 is equal to 12. So BC is equal to 12 with tan 45, which is 12 meters. Do we have enough information now to calculate CD? Do we have enough information now to calculate CD? Yes. We have two lengths and an included angle. You see that, people? Let's take this off here. Beautiful the sum, eh? And again, all sums are beautiful. So this angle is, if this is BCD, that is 55. What else do we have? BC is 12 and BD is 14.3. Okay. So what do I say? In triangle CDB. People, do I have to say this here? Do I have to write this in the side? Okay, I'm just taking it out so that you guys can be more comfortable with this. Okay. So we say CD squared is equal to BC squared plus BD squared minus 2BC times BD cos of CBD. Do I have to write it out like this? No. Okay. But let's go. We've got CD squared equals 12 squared plus 14,3 squared minus 2 times minus 2 times 12 times 14.3 cos of 55. So 14.30 was the last calculation value we calculated there, or the answer calculated. So it's 12 squared plus answer squared minus 2 times 12 times answer cos of 55. Give an answer of 151,65. But you must take the square root there, not so. Square root answer gives you an answer of 12,31. meters. Okay. Is there any confusion there? Easy, no? Nice. Let's carry on with our lives. Here's a note here somewhere. Okay, we are told that three-dimensional problems can involve prisms and pyramids, which you have worked in grade 10 and 11 with. Okay, remember that right angles will not always look like right angles. Okay. Did we do measurement last year? Huh? Yes, okay. These things. We did this also, yeah. This one in particular we did in grade 9. You should have done this in grade 9. Alright, so we're looking at this work example here. This is on page 126. Okay. The figure shows a cube with sides 20 millimeters. So if it's a cube, people, that means to say that all the sides are the same. Okay. If it's a cube. So there's 20, 20, 20, 20, 20, 20, and so on. Okay. Calculate the angle that the plane ABR is. ABR is. So this is what you should see. ABR is. Okay. Calculate the angle that the plane makes with planes with this flat surface. Okay. ABCD, which is this one here. So the angle in question is this angle here. Did you see that, people? Don't see it. What's wrong with you? You should say many things. You don't see it now, then I. Okay, let's go again. So plane A, B, R, that one there, no? Imagine a block of wood. You cut that from one point of the wood to the other point. Then he was going to get something looking like this. No? So this is what you should be seeing here. That's when you cut that thing through like. Okay? Where that triangle is this triangle. Okay? Then the plane A, B, C, D. Right. Oh, the D's are the wrong way. That's why you're confused. No? The D's there. Huh? But anyway, so what happens is the angle that they are referring to is the angle between the plane and the horizontal plane, and that move going up there. That is the angle they want you to work out. So in other words, this length here, which is CR, then this is BR, and this is angle theta. You see that, people? But what's the length of CR? 20. BR? BC? 20. So what is theta? Huh? Come on, people. Okay, well, how can we work out theta? Why? Yes, angles opposite equal sides. A sausage triangle. So for those of you who are not following, people, RC is equal to BC, which is equal to 20 millimeters. Not so. Then the angle theta is this angle here, which is there. So tan. So tan of theta is equal to 20 over 20, which is 1. Arctan of 1 is 45 degrees. Not O, theta. Right, you got it now? Alright. So theta is 45 degrees. And put 45 here. Let's go to the next question. Next question says, one is running front. The next question says, calculate the angle diagonal BS. BS is nothing about the sun, no? He says the diagonal BS makes with plane ABCD. Now where's BS? You want to use purple. Okay. So B is make sure the plane A, B, C, D. So it's what's on the ground, the horizontal plane. So in other words, how am I going to conclude this triangle? It's going to be B, S, D. Why D? You got your 90 degrees here. What else do you have here? Huh? S? B. How do you have S, B? Is D. You can calculate is D. How? Is D. Is D. Oh, yes. Sorry, man. Sorry. That D is not on the right way, I'm telling you. Make me confused. Right. D is what? Okay, here we go. The angle they want to us to calculate is called alpha, and then this is B. But to calculate this angle, what do I need? I either need SB or DB. Which one of the two can I calculate at this stage? BD is what? So the diagonal is of the plane here. If you look at this here, remember what shape is ADCB? What type of shape is this? A square. This is all 20, not so. This is 90. Now DB is this length going down again. Now that is 20. This is going to be 20 root 2. That's off this triangle. Say you didn't know that. So now you're going to calculate BD by using Pythagoras. So it's going to be 20 squared plus 20 squared, which is 400, is 800, and the square root of 800 is 20 root 2. Are you all okay with that, people? This was a square. Okay, so that is 20 root 2 then. So how do we calculate that angle alpha? Sorry? 10. Again, that's opposite and adjacent. So we say 10 of alpha equals opposite, which is 20 over 20 root 2. So alpha is equal to arctan of 1 over root 2 or 20 over 20 root 2. Arctan. And I answer 35.26. Is there any confusion there? Huh? No. Okay. So that brings us to the end of the examples for exercise 3 on page 126. Are you guys okay with this, or must I do another example? Okay. So I'll start the exercise then now. Okay.